So in the last section, we introduced this new idea of critical values, and hopefully you left that section with an understanding of critical values and maybe the ability to, if given a graph like you see right here, identify all the different critical values. We learned how to do that both algebraically and geometrically, but for the sake of this example, I want you to do it purely geometric. Ignore the fact that the pictured graph is x squared sine of x, and see if you can find the critical values just by looking at the graph. If you were thinking that there was a critical value somewhere around here on the graph, and then also somewhere down here on the graph, and up here on the graph, down here, and also up here, that's fantastic. But if those are the only ones you found, you're actually missing one, because there's a critical value here at 0 as well. When we talk about critical values, we're talking about points where the first derivative equals 0, and technically the first derivative could also be undefined, although that's not going to be super important for our class. And since the first derivative represents the slope of the tangent line to the curve, and a line with a slope of 0 is a horizontal line, we're just looking for all the different points where, if you were to draw a tangent line to the graph at that point, that line would be horizontal. And for most students, it's fairly obvious that we'd have a horizontal tangent line up here, for example. But maybe it's less obvious that we'd have a horizontal tangent line at 0. But once somebody points it out, you're like, yeah, I guess if I were to draw a tangent line, it does get flat right here. So maybe you're convinced that pictured are, 6 different critical values and not just 5 of them. You may be wondering why we care so much about critical values. Well, critical values kind of come in 3 different flavors. A critical value can either be a local minimum, a local maximum, or neither a local minimum nor a local maximum. You may not even need me to define those terms for you, but I'm going to do it anyways. When we talk about a local minimum, we're just talking about a point whose height is less than the height of all of its immediate neighbors, loosely speaking. So this point right here would definitely qualify as a local minimum, because if you go a little bit to the left here, you're higher up, and a little bit to the right, you're higher up. We're at the bottom of a valley, loosely speaking. That's not to say that this is the lowest point on the entire graph. For example, there's a point over here that's lower than this point that we're talking about. And for that reason, we have to add this qualifier as local. I'm not saying that this is the minimum point on the graph. I'm just saying it's smaller than all of its immediate neighbors. Similarly, this point up here we'd call a local maximum, because this point is higher than any of its immediate neighbors. It's not the highest point on the graph, but it's higher than anything right next to it. Not necessarily the smartest kid in the world, but maybe smarter than all of his classmates. I don't know. That was kind of a dumb example. Anyways, the point is this is a local minimum and this is a local maximum. But critical values like this one that was kind of tricky is neither a local minimum nor a local maximum, because if you go a little bit to the right, you're higher than this point. And if you go a little bit to the left, you're lower than this point. On this specific graph, we have local maxima at this point between -4 and -6, at this point a little bit greater than 2, and at this point a tiny bit greater than 8. And we have local minima at this point between -2 and -4, and at this point between 4 and 6. And the critical value at 0 is neither a local minimum nor a local maximum. Before I move on, so I don't forget to say it, instead of using the adjective local, some books use the term relative. It means the exact same thing. You call this a relative max or a local max, either way means the exact same thing. Anyways, in the last section, when we talked about critical values, we talked about them on the graph, but we also kind of played in this situation where, what if you don't have the graph and just have the equation? Could you still figure out the critical values? And you were like, yeah, no problem. All I had to do was take the derivative and set it equal to 0 and solve. And technically, we should have looked at when the derivative is undefined, but seldom will the derivative be undefined in our class, so that's kind of a special case that we can basically ignore at this point in the class. We're really just interested in when the first derivative is equal to 0. If we had the algebraic skills to take the derivative of this function, set it equal to 0, and solve, we'd get infinitely many solutions, but the ones within the range pictured would be the x-coordinates corresponding with all the little dots I put on this graph. Whether you have the graph or not, it's relatively easy to locate critical values. But classifying those critical values as either a local minimum, a local maximum, or neither, if you don't have the graph handy, is a lot more challenging. We didn't learn how to do that in the previous section. That's going to be kind of the main topic for this entire section. We already know how to find the critical values, but without graphing them, how can we tell what flavor critical value we're looking at? Well, it turns out the key to doing so will be looking at derivatives. And there's 2 different ways to use derivatives to classify critical values as local minima, local maxima, or neither. The first way is using the first derivative. So we already know that because this point right here is a critical value, the first derivative equals 0 at this point. At this x-coordinate, f prime of x equals 0. And the same is true for the rest of our critical values. That alone doesn't let us figure out whether the critical values are local minimums or local maximums, but if you look at the first derivative on either side of your critical values. So think about the first derivative to the left of this critical value. I claim that f prime of x over here must be greater than 0. How do I know that? Because the graph is increasing as I read it from left to right to the left of this critical value. Similarly, because the graph is decreasing to the right of this critical value until I get to this next critical value, I know that f prime of x is less than 0 on this little interval. To the left of this critical value, the first derivative is positive. To the right of this critical value, the first derivative is negative. This critical value happens to be a local maximum, and that's not a coincidence. Anytime our first derivative changes from positive to negative at a critical value, we must have a local maximum. Because think about it, if you're a hiker approaching that critical value from the left, and your first derivative is positive, you're coming uphill. And then once you pass this point, if your first derivative turns negative, you start going downhill. So you're going uphill until you got to the point, and then you turn around and you're going back downhill. That means that point is a, mountaintop or something. In other words, it's a relative maximum. And the exact same logic works for relative minima. If our first derivative switches from negative to positive, like it does at this critical value, that means we used to be going downhill, we stopped at the critical value, and we started coming back uphill. Anytime your first derivative switches from negative to positive, that critical value must be a local minimum. But look at this next critical value. To the left of this critical value, our first derivative is positive because we're going uphill. We get to this point, we have a brief rest, but then we just immediately start going uphill again. Our first derivative switches from positive to positive at this critical value. Our first derivative is not changing sign. That means we don't have a local minimum, nor do we have a local maximum. When your first derivative does not change sign, you still have a critical value. That critical value is just not a local minimum or a local maximum. Remember, this point is a local maximum because the first derivative changes from positive to negative. Maybe you're convinced that anytime the first derivative changes from positive to negative, we'll have a local maximum. Let's see. The first derivative is positive to the left of this critical value, and then it's negative to the right of this critical value because the graph is decreasing. And sure enough, this point is a local maximum. Similarly, at this local maximum up here, to the left of the point, our first derivative is positive. To the right of the point, our first derivative is negative. The same criteria that we saw over here, the same type of critical value, a local maximum. And much like this local minimum showed up when our first derivative changed from negative to positive, this local minimum, we also see the first derivative changing from negative to positive. One way we can classify critical values as local minima, local maxima, or neither is by considering the first derivative on either side of the critical value. That's something that we're going to call the first derivative test. And written a little bit more carefully, what it says is if the derivative of a continuous function changes from positive to negative, that point where it changes is a local maximum. You can memorize this statement if you want, but really you don't have to. You can just kind of think about it. If my first derivative is changing from positive to negative, that means the graph used to be going up and now it's coming back down. What would that look like if my graph used to be going up and now it's coming back down? It would look like a mountaintop. It would look like a local maximum. Similarly, if the first derivative changes from negative to positive, we used to be going down, now we're coming back up. That point where we change signs would be a local minimum. That's your first derivative test. You don't really have to memorize it because it's very intuitive. It makes a lot of sense. It always works. There's no trick cases you have to worry about. The first derivative test is great. Kind of. The problem with the first derivative test is it's a little bit tedious to use. The reason it's tedious is because we locate our critical values, but we can't just look at the critical value to figure out if it's a local maximum or a local minimum. We have to look to the left of the critical value and to the right of the critical value. We have to incorporate this idea of the first derivative changing sign, either from positive to negative or negative to positive. And algebraically, that's a little bit tedious. It's a little bit annoying. Fortunately, there's a solution. If we go back to our picture here and look at this local maximum and this local minimum, and look for other differences between the shapes of the graphs at those points, you might notice that at this first critical value, my graph is concave down. It looks like an upside down cereal bowl. Whereas at this second critical value, my graph would be concave up. I could absolutely eat cereal out of this thing. That's kind of cool. It would be neat if anytime I had a local minimum, my graph were concave up. Let's see, we have another local minimum over here, and sure enough, my graph is concave up at this point. What about my other local maxima? Are they always concave down? Yeah, absolutely. Think about the shape right here at this local maximum, or the shape over here at this local maximum. It kind of seems like anytime my graph is concave down at a critical value, that critical value is going to be a local maximum. And anytime my graph is concave up at a critical value, that critical value is going to be a local minimum. And it turns out that's true. And if you kind of think about it, it makes a lot of sense. Because concavity is talking about your second derivative, right? And the second derivative is just the change in the first derivative. So if the first derivative is changing from positive to negative at this critical value, that means your first derivative is getting smaller. If your first derivative is getting smaller, then your first derivative is decreasing. If your first derivative is decreasing, then your second derivative is negative. I can interpret the fact that the graph is concave down here by thinking about the first derivative is getting smaller. And since I know at this point the first derivative is 0, if it's getting smaller, it must have been positive to the left of this point and negative to the right of this point. Same logic works with a critical value where the graph is concave up. Instead of thinking about the function being concave up at this point, think about the derivative of the function increasing at this point, because the second derivative is just the derivative of the derivative. It's the change in the derivative. So you can think about it two different ways, either the shape of the function or the change in the derivative. If we interpret it as the change in the derivative, it means the derivative is getting bigger at this point. We know at this point the derivative is equal to 0, and if it's getting bigger at this point, that means before this point it must be negative, and after this point it must be positive. Really, encoded in the first derivative test is this thing called the second derivative test. And what the second derivative test tells you is that if the derivative of a function is 0 and the second derivative is negative, that point must be a local maximum. And if the derivative of a function is 0 and the second derivative is positive, that point is a local minimum. And much like the first derivative test, you could totally memorize those statements if you want, but I claim you don't have to. Because just think about what it would look like to have the first derivative be equal to 0 and the second derivative be negative. If the second derivative is negative, that means your graph is concave down. Concave down means it has this shape right here. If your first derivative equals 0, that means the tangent line at that point is horizontal. In other words, we're talking about this point on the graph. This point represents a local maximum. Similarly, if your second derivative is positive, we're talking about a concave up graph. And as long as you know that a concave up graph looks like this, it's easy enough to locate the critical value, this point down here, and conclude that we'd have a local minimum when the second derivative is positive. I guess it's a little bit counterintuitive that negative second derivatives correspond with maximums and positive second derivatives correspond with minimums. You might think minimums are negative and maximums are positive, but it's not. And the second you consider the shape of a concave down or concave up graph, that fact becomes immediate. At this point, you're probably thinking, oh, the second derivative test is way better. I don't have this tedious idea of having to look on either side of a critical value. I can look at the critical value itself and just consider the second derivative. That's awesome. Yeah, that is really awesome. And you talked about when the second derivative is negative, I have a local maximum. And when the second derivative is positive, I have a local minimum. I bet anytime the second derivative is 0, that critical value is probably neither a local minimum nor a local maximum, right? Is that what's going on here? Unfortunately, no. Well, it's true that the second derivative at this point is equal to 0. The fact that the second derivative equals 0 does not guarantee that this point is neither a local minimum nor a local maximum. The big downside to the second derivative test is sometimes it fails. But that sounds a lot worse than it really is. All you have to know is, if you're trying to use the second derivative test, you're going to look at the second derivative. If that second derivative is negative, that means you have a local maximum, done. If the second derivative is positive, that means you have a local minimum, done. If that second derivative equals 0, what you need to know is that does not necessarily mean that that critical value is neither a local minimum or a local maximum. If your second derivative equals 0 at a critical value, that means the second derivative test fails, meaning it gives you no information about whether that point is a minimum, a maximum, or neither. The best counterexample to that thought is if you consider f of x equals x to the 4th power. I'll let you work this out if you want, but if you do, I think you'll see that you have a critical value at x equals 0, and that critical value is a local minimum. But if you try using the second derivative test to come to that conclusion, it won't work. F double prime of 0 is equal to 0, and what that means is the second derivative test fails, But if you look at the graph of y equals x to the fourth, what you'll see is it kind of sort of looks like this, a lot like your standard parabola, but a little bit steeper kind of. That critical value is definitely a local minimum, even though the second derivative at that critical value equals 0. All I'm saying is second derivative test is typically the one you're going to want to do. And when you're using the second derivative test, just hope that your second derivative is either a positive number or a negative number, and then you get your answer immediately. But just know that if you're unlucky enough to get a value of 0 for your second derivative at a critical value, that critical value might still be a local min or a local max. And probably the best way to figure it out at that point is to revert back to your first derivative test. The more tedious way of doing things, but one that always works. That's the idea behind the first and second derivative test, which will be the main topic of 4.3. We'll work through some examples showing you how this works in practice in the next video.